Good day, grade 11s. Today we are talking about the molecular formula and the empirical formula. So the molecular formula is what you are used to in the sense that it's just the normal formula of a molecule. So whatever the molecule is in its formula, that is the molecular formula. That's what you've been using all the way until now. The empirical formula is a little bit different. That is the simplest whole number ratio of the elements making up the molecule or the compound. Okay. So in many cases, especially with simple molecules, the empirical formula and the molecular formula will be exactly the same. An example of this would be something like ammonia. The molecular formula, let's just say M, and let's just say E. The molecular formula for ammonia is NH3. As you can see, it cannot be divided into a smaller ratio, so its empirical formula is also NH3. Another one, everyday life molecule is water. You can see it cannot be divided into any smaller ratios. Another example of this, well, these are all then molecules that have the same empirical formula and molecular formula. But if we look at others that works a little bit differently, is something like hydrogen peroxide, H2O2. This is molecular formula. Its empirical formula is HO because it can be divided into a simpler ratio, and this is the simplest ratio. Another example of this would be, let's say, C2H6, and that is something called ethane. It's an organic compound. Its simplest ratio, its empirical formula, will be CH3. Okay, just to explain the basic concept regarding this. So the rest of today's video would be focused on doing calculations, like how to determine the empirical formula and also the molecular formula. And we are going to do that by understanding that the different elements represented in a molecule or like in the empirical formula, it will follow a specific mass ratio. Okay, so we're going to use this by using mass, and I'll explain that more now by using an example. So let's say, for instance, a question is stated and they tell you, okay, we have a compound and we know that it has this amount, like percentage wise, of its carbon, and this percentage wise is hydrogen, and that percentage is oxygen. What is the compound? Like, what is the molecular formula? What is the empirical formula? Questions like that. Now, our tools for this would be the following: moles equals mass divided by molecular. So this is your first tool in this calculation. The second one is the information was given in percentage. So in percentage, we know full marks is 100%, right? So the total sample is representing 100%. So let's say, for instance, you've got 3 compounds, and they give you the percentage. You are going to assume 100-gram sample, so that the percentages will just be grams. Remember, we are working with ratios, so it doesn't matter if we take 100 grams or 100 kilograms, but 100 grams is easy to work with because our molar mass is grams per mole, and that's what we are going to work towards. Okay, so the example we are working through is example 1 in your textbook, Study Master, page 190. And it's example 1. We're working through the same example. I'm going to explain it step by step. So they give us the following percentages: 44.86% potassium, 18.42% sulfur, and 36.72% oxygen. And they are asking, what is the empirical formula? Remember, I told you the key to this will be to assume 100-gram sample. Okay, so if we take the three different compounds or elements, we take potassium, sulfur, and oxygen, and we are assuming 100-gram sample. Then we can use the percentages as mass. So here we can just say gram per 100 grams. So the potassium is 44,86, sulfur is 18,42, and oxygen 36,72. Okay, remember we are working towards molar ratio, because for molecular formula, empirical formula, all of them are set up in a molar ratio. We're not looking at mass, we're looking at moles. Okay, so the next thing we are going to need is the molar mass of each of these elements. So you use your periodic table to determine that. So for potassium, it is 39.1. For sulfur, it's 32.1. And for oxygen, it is 16. Remember, this is now grams per mole. So if this is the sample size, we assume per 100 grams, right? So that we can use the percentages. And we have the molar mass of each of these elements. We can calculate the moles. Now, for the sake of space, I'm not going to do the calculation in the table. I'll do it here at the bottom. And then just write down the answers over there. So, for potassium, mole equals mass divided by molar mass. And that was 44,86 divided by 39.1. And that gives you 1,15. Okay, so for sulfur, same formula. We have 18,42 divided by 32.1, and that gives us 0.57. And then for oxygen, we have 36,72 divided by 16, and that will give us 2.3. Okay, it's clear over here. You can see mass wise, potassium was the most, right? You can see the 44,86, right? And oxygen 36.72. But mole wise, there's double the amount of oxygen than potassium. And sulfur, smallest mass, but also smallest molar ratio. Now we're going to fill this into the table, and then I will take it further from there. So 1,15 is 0.57 and 2,3. So this is now the ratio, right? But we are interested in whole numbers. We cannot work with the 1.15. We need to determine the molar ratio, right? And the way we are going to do this is we are going to take each amount of moles for this 100-gram sample, and we are going to divide it by the smallest number. You can see here 0.57 is the smallest number. So in order to get the ratio, that's what we are going to do. We're going to say 1,15 divided by 0.57. 0.57 divided by 0.57. 2.3 divided by 0.57. And then we're going to write down the answers. If you do this calculation sheet, it's 2. If you do this one, it's 1. One of them will always be 1, so the smallest one will be 1. And if you do this one, you get an answer of 4. So what we know then from this calculation is that it would follow the following ratio. For potassium, there will be 2 of them. For sulfur, 1, which we're not going to write. And for oxygen, 4. So you can clearly see that the sample we have been working with is potassium sulfate. And this is the empirical formula. Now, and they didn't ask anything about the molecular formula. Okay, now we're going to move on to an example to calculate the molecular formula. So the next example reads as follows. Calculate the molecular formula of the basic amino acid lysine if the percentage composition is 49.31% carbon, 9.55% hydrogen, 19.18% nitrogen, and 21.92% oxygen. But now additional information is given, and you will always need this additional information if you need to get the molecular formula. And they say the molar mass is 146 grams per mole. If they don't give you that information, you can't go from the empirical formula to the molecular formula. And I will show you now that the calculation looks exactly the same for empirical formula and molecular formula all the way till the end, and then there's just one additional step when you get to the actual calculation for the molecular formula. So just to save time, I'm going to do the calculation and just show you the final result. Okay, so here's the calculations. I'm just going to talk you through it, and again it's exactly the same as the empirical formula. That's all the way till where we are now. Okay, so here we have our grams per 100 grams. That's based on the percentages above. As you can see, I just followed the exact same numbers. This is the molar mass for each element that you get from the periodic table. Now we calculate the moles, and there are the answers for the moles. And then we use these numbers divided by the smallest one of them, which is 1.37. So 4.11 divided by 1.37 is 3. Same over there is 7 and 1 and 1. Okay, so now we are at a place where we can write down in the following order. We can say C3, H7, NO. That's the only thing we know about this one now. So this is technically the empirical formula, right? But now to go from this one to the molecular formula. So what we're going to do is we are going to calculate the molar mass for this compound, and we are going to compare this molar mass with the molar mass given. Okay, so 3 times 12 equals 3 carbons, right? Plus 7 times 1, 7 hydrogen, plus 1 nitrogen, which is 14, and plus 1 oxygen, which is 16. Then you can just calculate this. That's a 30, that's 36, so it's 66. Plus 7 is 73, right? 73 grams per mole. And now we're going to compare this with the molar mass given. So the molar mass given was 146 grams per mole. So that means, okay, this is 73. How many times does 73 go into 146? Well, it goes into 146 twice. So that means whatever the numbers are here, to get from the empirical formula to the molecular formula, we have to times by 2. So our molecular formula is C6H14 N2O2. And that's it. That's the molecular formula. Just one last thing from my side. If these numbers over here are not whole numbers, you have to multiply again. Let's say this 3 was a 2.5, then you would have multiplied everything with 2. And that would have become a 5, and there's a 14, a 2, and a 2. So just keep that in mind. These have to be whole numbers.